Okay, so yeah, thank you everyone for coming back for another talk. So today we have Rajika Kuruwita, who I first met nearly 10 years ago.
Yeah.
And we were both PhD students at Mount Stromlo. She then went on to do postdocs at Copenhagen, then Heidelberg, and has now come back to Mount Stromlo to do another postdoc. Yeah, mainly doing everything to do with binary star formation and some exoplanets, I guess. So yeah, take it away.
Yes, thanks, Alex, for inviting me. Yes, I generally do binary and multiple star formation. This is an image from one of my simulations of zoom-ins. As a co-author in Nature. I really love this image. It was a failed cover, so I just plaster it on everything. I always wanted to be an exoplanet person. But kind of the way that my career path fell, I just went into star formation. But, stars and planets, they form together, and I often try and use exoplanets to motivate a lot of my research. So today, yes, I'll generally talk about binary and multiple star formation, but specifically I'll talk about how do stars get their spin? And I'll really go into details about some work that was published in 2024 with this boring title, which is Protostellar spin up and fast rotator formation through binary star formation. And if you really want to check out the paper, you can go to this DOI or just look it up. So over my talk, I'll give you some background about star formation and multiplicity. And then I'll go into the spin evolution of stars, what we know of how stars get their spin, and then the work I did in Kuruwita et al. 2024, and just some future work that is built on what I just published. So binary and multiple stars and planets and binaries and multiple stars has sort of been a trope of science fiction for quite some time. You're aware of this planet, Tatooine, in Star Wars, and this is from Futurama, which has 3 suns. And yeah, they've kind of been a trope for a long time, but in the age of Kepler and TESS and other space surveys, we have been discovering more and more exoplanets every day. And I just checked a few weeks ago, and we have surpassed 6,000 known exoplanets. And with these, we are starting to find that, understand the demographics of exoplanets. And we have actually discovered about 500 or so exoplanets in binaries. And a lot of them have an orbital configuration kind of like this, where the two stars are quite far apart and the planet goes around one of those stars. And that's a pretty stable configuration as long as the other star is far away. It basically looks like a single star. And we've also discovered about 30 or so circumbinary planets. So this is where the two stars in the binary are quite close together and the planet orbits both of those stars. And that's, again, is also quite stable as long as the planet doesn't get too close to the inner binary. So we know that, some of these planets of science fiction, they exist, but we don't know a lot about the likelihood and whether we should even care. And I will argue that we should care about planet formation in binaries and multiples, given that most stars exist in binaries and multiples. So this is from the Protostars and Planets chapter from Stella Offner. So here the x-axis is the mass of a star, and the y is the fraction of those stars that are in binaries or multiple star systems. And what we see is that basically all massive stars have a companion. And for stars like our sun, about 50% of them have another star around them. So this is looking at basically all the stars, so main sequence and post-common envelope and whatnot. So yeah, we see that a lot of stars exist in binaries, but we see that, this is from JWST looking at the Carina Nebula, stars form in these dense environments. You have magnetic fields that sort of carry gas, these dense ridges and there's also turbulence making it messy, and eventually you get these clumps forming. And you might get an overdensity kind of like this one here, and gravity will start to overcome the pressure of the gas and form a star. So the typical picture of how a star forms kind of starts off with this. You have what we call a pre-stellar core, and that starts to collapse. And as it's collapsing, it's also rotating. So because of magnetic fields, we start to get these jets occurring, and we have this protostellar disk. And as it continues to evolve, the envelope is sort of all accreted. Then we get left over with more of a disk. The cavities are opening, and then eventually the disk starts to dissipate, and you get this debris disk, and you get planetary systems. And this is a really nice picture of star formation. But simulations and observations are kind of finding that a typical prestellar core like this, on average, fragments and forms 2 to 5 stars. So that already messes up the picture. And looking at observations, we actually see that most stars are born in binaries. So this is observations of mostly main sequence stars in the class 0, 1, and main sequence phases. And what we see is that 2/3 of stars are born with a companion, and this fraction of frequency decreases as they evolve towards the main sequence. So what we're seeing here is that there are these young multiple stars that are forming, and they interact with each other and disintegrate as they evolve towards the main sequence. And while these interactions are happening, the stars host protostellar disks, which may become protoplanetary disks. So these interactions probably definitely impact the sites of planet formation. So these are some questions that we should think about when trying to understand, the demographics of the planets that form. So in this talk, I'm going to focus on some work I did looking at stellar spin. So I'll just give some background about stellar spin, because I actually didn't know a lot about this until this question was posed to me by an astronomer. So what we know of stars and their spin. So this is just like the mass of a star, spectral type, so low mass and high mass. And this is a measure of the spin of the stars. And what we see is that very massive stars, they spin very quickly, and kind of lower mass stars, they don't spin as fast. And this transition here kind of is because of the transition from having a radiative core in small stars to a convective core in massive stars. But for the rest of this talk, I'm actually going to focus on the low mass end. And oh, by the way, I can't see the video, but if anyone wants to interrupt, just speak up over me, and I can try and answer any questions as we go along. Yes, so low mass stars. I'm going to focus on the low mass star. And what do we know about the spin evolution of stars? So this is some plots from Gallet and Bouvier from 2013, and they basically plot like the spin of stars against age. So this is the first, 0 to 5 million years is kind of the typical time scale for star formation, maybe stretching it out to 10,000 years. And then over the next, few hundred million years, that's like the main sequence phase. And this is, the spin, and these are data points, and the sun is over here. So this is the age of the sun, 5 billion years, and its spin rate is about 5. Yeah, no, sorry. 25 days. Yes, it's a bit of a slower rotator. And we can sort of kind of broadly group the spin evolution of stars into like this red line up here, which we call fast rotators, and this, the blue line up there, and the red line down here, which is called slow rotators. And there are sort of 3 phases of the spin evolution of stars. Initially, we think that the spin evolution of a star is pretty steady, and that's because of disk locking. So in the early stages, you have this star, and in the really inner disk, everything is ionized. Whoops, sorry. Let's go. Can I go back? Sorry, it's not letting me go. There we go. Everything's ionized, so you have very strong coupling between the magnetic field. So basically, the magnetic field threads through the inner disk, and because of that, the star might want to spin up because it's contracting, but also the disk is further out, so it spins slower. So there is this tension, and because of that tension, we also that leads to angular momentum loss through winds being launched. So we think at this point, the spin evolution of the star is pretty steady. But then once the disk disappears, the protostar is still contracting and it's going to spin up. And it's a typical ice skater, you know, when you bring your arms in, they start to spin up faster and faster. So this is what we think is happening in this second stage. And then after it's basically finished forming, it lives out its life, but it spins down very slowly because of magnetic braking within the star. You know, angular momentum is lost through ionized particles in the solar wind. And then eventually the spin of the stars, low mass stars, all seem to kind of converge towards where our sun is at. So these are the models, but what do observations say? So these are some observations of TESS stars, I think, from Sana et al. And there's a whole lot of scatter. The blue points are observations, but if you bin them and you take an average, you kind of get this spin down. So the V sin I goes down, but then it starts to go back up. And what they think they're seeing is when the average spin is going down over the first 5 million years. This is because there is a disk present. So the blue dotted line is a model of spin evolution without a disk. And then once the disk disperses, we start to get the spinning up that we think should happen after the disk disperses. So that seems to broadly agree with these models. And then also from TESS, so Marina Konkel, she was looking at the spin evolution of stars. So L here is angular momentum, not luminosity. And what we kind of see is that so red is younger stars and purple is older stars. And we see this general evolution from like high spin to low spin over you know, many millions of years. So this is probably that slow spin down that we expect should happen. But these models were mostly looking at, I guess, the single stars and what Marina was finding that, oh, yeah, sorry, I was meant to have this plot, is that there were these fast rotators. They're low mass stars that had rotation periods of about 2 days or less. And what she was finding was, you know, she could fit SEDs. And for the stars that had rotation periods of 2 days or less, they were much better modeled with a binary sequence as opposed to a main sequence, which was basically saying like the SEDs were better modeled if there was an unseen companion nearby. And that is interesting because there's a few other lines of evidence that could suggest that maybe having a binary nearby could help create these fast rotators. So you might have noticed here that this straight line is shorter on the fast rotators than it is over here. And one of those things might be because in a binary, the disk is dispersed faster. So then that sort of slows down how much the star gets to spin down and then initiates that post-main sequence contraction faster. So yeah, so you might need a companion nearby to truncate the disks. And also there is evidence that fast rotators seem to have a lack of planets around them. And that could be a question of why don't we see planets around them? Is it because, you know, maybe the stuff to make planets is gone. It's been eaten up by something else. So this was presented to us by Marina, and she was wondering whether maybe binary star formation could inherently produce fast rotators. So that's one thing we thought would investigate, see like how stars get their spin and whether having a binary multiple could impact that. And the way I did that is I did simulations. So I used the Flash magnetohydrodynamic code. I started with a 0.1 parsec, like well, it was meant to be pre-stellar core because the star hadn't formed yet. So it kind of looks like this. It had a mass of 1 solar mass and it's rotating, and there was a magnetic field that's threaded along the x-axis. And I tested different levels of spin and turbulence. So sometimes I had the cloud spinning slowly, sometimes I had it spinning fast, and then also just like simulations with turbulence and without turbulence, because these pre-stellar cores, we observed them to have some subsonic turbulence. And then after we set up the simulation, we let the cloud collapse and then sync particles can form. So if you have an overdensity that we're pretty sure is going to form a star and it's not within the accretion radius of another sync particle, then it'll be replaced by a sync particle and then it can interact with other sync particles just by n-body dynamics. So I'll just show you the movies here. So on the top line, I have the simulations without turbulence, and the bottom I have simulations with turbulence. And on here we have the clouds that spin slowly, and on the right we have the clouds that spin quick. Was there a question? Okay. Sorry, I wasn't sure if I heard a question. The movie isn't playing right now. I'm just explaining what you will see. Yeah. Yes, and what you will see is a top-down view of these clouds spinning. So now I'll run them. So you can see in the non-turbulent cases, it's like a bit messy. There's a lot of seeding from the grid, whereas in the turbulent cases, it looks a bit more organic. Oh, sorry, yeah. But we got these clouds collapsing, and in the low spin cases, you had more of a disk, whereas in the high spin cases, you got like a ring forming because of the high spin. Sorry. Yeah, because the high spin, but you see like you have this primary star forming in the middle, but eventually within these disks you get these overdensities forming and we get companions forming. And then sometimes the core evolves into some pretty complicated systems. So I will say here that we get too much fragmentation because we do not take into account radiation. Radiation feedback would heat up the disk and kind of protect that against further fragmentation. But with that in mind, we can still look at how the stars get their spin. So I'll just go through what we saw in the simulations. So here I plot like the mass of the sync particles over time, and blue is low spin and red is high spin. So we kind of see that all the primary stars, they form initially and they accrete mass pretty quickly, but then they level off. But then at some time later, they all seem to have a burst of accretion. And that is correlated with the formation of companions. So these are all the other stars that formed in the simulations, which is interesting. So that was the non-turbulent case. This is a turbulent case. So in the turbulence case, the initial growth of the primary star is about the same, and then it seems to continue. It doesn't quite level off, but then they also experience these bursts of accretion later on, again, sort of correlated with the formation of companions. So this is the mass of the sync particles. But we're interested in the spin, so let's look at the angular momentum. And here we have the angular momentum of the primary star, increases and it levels off, and then we have these bumps in angular momentum. Again, correlated with the formation of companions. And you're probably thinking, it's the same with the turbulence as well. The shapes are very interesting. They basically are following the same trend, and that makes sense because angular momentum is mr cross v. So the angular momentum is proportional to the mass. So what we are interested in is the period of the star. And assuming solid body rotation, a period of a sphere is basically given by the radius of the sphere and the specific angular momentum. So it's just the r cross v. So what this tells us is that basically the period of the star is inversely proportional to the specific angular momentum of the sync particles. So if we plot that, we get this. So in the non-turbulent case, we get the primary stars, they spin up very quickly and then they sort of level off. Some of them even seem to trend down. And then you have these little bumps, these spin-up events, again, happening when the companions form. In the turbulent case, you get the spin up pretty quickly. And then, yeah, you get these spin-up events that happen later on. So that's curious. And I want to quantify these spin-up events. So I just sort of compare, the spin post-event and pre-event. So I just take this delta H and just calculate a percentage of how much this span up. And what I plot is here. So these are like the simulations with turbulence, and these are the simulations without turbulence. And what we see is that in some of the simulations, the star can spin up almost 20% in one of these spin-up events. And in other cases, it was only a few percent. So that was neat, and I wanted to figure out what exactly is the mechanism that's causing these spin-ups. So I look at the two extreme cases. That's the easiest one, and really look at what's going on around these stars. And I wanted to investigate the spin-up mechanism by looking at the Tourmaire Q, because we noticed that the spin-up was correlated with the formation of companions. So I look at the Tourmaire Q because this is a measure of how stable the disk is. The Tourmaire Q is basically given, it's a ratio of like how rotationally supported a disk is versus how much gravity is trying to bring it in. And if Q is above 1, then it's stable. So you have more rotational support. And if it's less than 1, then it's unstable. You have more gravity kind of pulling things in. So this was a hydrodynamic sort of definition, but we have magnetic fields, and that provides an extra level of support. So I actually calculate the magnetic Tourmaire Q. And that's what I look at here. So here I look at detail of the spin-up event. So this is before the spin-up event of the primary star, and you'll see that this pointer will move across, and the spin-up event really happens here, and then it levels off. So initially we had this primary star here. We have this nice protostellar disk. And over here, this is the magnetic Tourmaire Q. So the white kind of means it's marginally stable. Red is the places where it's kind of unstable, and the blue is the places where it's really stable. So we kind of already see that there is this arm. It's there in the density, but it's much clearer in the magnetic Tourmaire Q, which is like looks like it maybe could fragment. So let's see how this goes. So this unstable arm kind of rotates a bit, and then they really the waves sort of really crashed into each other, and the spin up event was triggered from those unstable spiral density waves just connecting with the primary star and dumping mass onto it. So we can see. Yeah, then the spin up really starts to kick off over there. We just have mass coming in. And then companions actually formed from the instabilities. So that was curious that the spin up event actually is initiated before the formation of companions in this strong case. In the weak case, so this is the same density color bar. So we see that the primary star is here, and there's actually already other companions that are outside the box, and they formed from ring fragmentation. But yeah, we have the circumstellar disk, which is slightly lower density. Whoops, sorry, I just want to compare that. And this is the spin-up event that we see here. It's a bit more jagged, so you'll see that the primary star will start to spin up and then slow down. And the degree is not as large. And yeah, here again, we see that the material around the primary star is marginally stable. So it's not, super stable, super unstable, but we'll see what happens. So what you'll see is that a companion will fly by. One of these companions will come by. And that makes the disk quite unstable and dumps mass onto the primary star. And that was actually what triggered the spin up. And then eventually this companion that flew by is kind of bound in a tighter orbit. So that was pretty curious. And what do we find from this? Well, we kind of found that the spin up events were in general caused by gravitational instability in a disk. And the strong spin-up events was caused by gravitational instability in like a more massive disk, which dumped high angular momentum material into the inner disk. And then it was actually from that strong instability that we got new companions, which is curious. In the weak spin-up case, it was also gravitational instability, but it was caused by a flyby of a companion. So the flyby kind of perturbed the disk, dumped high angular momentum material into the inner disk. and it didn't produce any new companions. So that was an interesting find. But we are ultimately interested in the rotation period of the stars. These models, they give an insight into maybe the evolution of the protostar, but actually our sync particles are quite big. So the resolution, it's like 2 AU, bit under that. So we're not actually tracing the protostar. We're tracing the protostar and the inner disk. So, we've got to be cautious about what conclusions we're making. So we try and do a resolution study. So this is the mass evolution, angular momentum, specific angular momentum, and period. And what you kind of see, purple is the highest resolution, blue is the lowest resolution. The mass evolution of the primary star is not converged, angular momentum not converged, specific angular momentum not converged, period not converged, but it is going further down. So the period is going lower and lower as we get to higher and higher resolution. So the highest resolution, sync particle size was 1.2 AU. So we can kind of use these trends to extrapolate down to the surface of the protostar. So we take a typical protostar radius, like low mass protostar radius of about 2 arcsun. That seems to be appropriate based on pre-stellar evolution models. And if we can start to resolve down to the stellar surface, which is these gray lines, we can start to approach the 2-day period that defines fast rotators here. So we kind of we use this to derive, what percentage of the accreted quantities in our sync particles is actually going into the star, the protostar. And you can look at the paper for some complicated derivations, but we can kind of apply that to really get the mass evolution of the protostar, of the primary star. And we have these very large spreads. So we think at the end of our simulations, our primary star is still pretty low mass. So 0.05 solar masses. The angular momentum is still being accreted. The specific angular momentum, the trends are the same, but the values are lower. But the periods, so yeah, you have the cloud collapsing, the protostar spins up, so the period decreases. And it's still above the definition of a fast rotator. But then once we have these spin up events, that does bump down the period of the star, kind of borderline of fast rotator, maybe even a bit lower. So, it could be suggesting these spin up events could help spin up the star and we can get these fast rotators. So looking at that, we sort of extrapolate our conclusions. So we have this event, you have the strong GI causing companions to form. And, if you couple that with having multiple sort of spin up events by flybys from this companion, and also truncation of the primary circumstellar disk leading to a short disk lifetime, maybe you could get some fast rotators. So we suggest that, having binary star formation could help spin up the primary star. But with our resolution of our simulations, we can't confirm that we can get these fast rotators, but we do think that this is a pathway to producing fast rotators. So this is the work that was published in 2024, and I've been wanting to build on this. So using the resimulate method from Yang and Federath 2025, I wanted to try and study the impact of the kind of star forming environment on the spin of stars. So with the resimulate, we can kind of cut out a box from these turbulent cloud simulations and then resimulate that at high resolution. So Christoph Federath has a cluster simulation with sync particles that form, and it's kind of low resolution. But here I plot the masses of the sync particles. The sync particles that he has are quite big. I forgot the radius of them, but we can't really be certain if one sync particle equals one star. So this is a thing that needs to be investigated. But we have This is just the masses of the sync particles from a simulation. This is the specific angular momentum. And I figured I'd have a look at the sync particle, this red one, because it accretes a decent amount of mass, and it becomes the second fastest star in the simulation. So this red line, and it's still preliminary work, but this is kind of what that candidate looks like. We sort of have this kind of fluffy prestellar core, which is neat. The blue lines is the magnetic field, and it collapses pretty quickly, so the color bar changes as well. But we get this sync particle forming in the middle. And when we look at what's happening closer to it, we kind of see that this candidate is being fed by this pretty prominent accretion stream. So accretion streamers have been pretty hot in the observations because we've seen them in simulations for a while, but now ALMA observations are starting to see these streams of mass kind of coming from large interstellar medium scales down to protostars, and maybe this is a way to replenish disk mass and cause accretion bursts potentially. But maybe this accretion stream is dumping high angular momentum material into the inner disk, and that is making the star spin up. So this is still work that I am running right now, and it'll be interesting to see the impact of the environment on the spin evolution of these stars. But I will leave you with my conclusions. So this was the main takeaways from the paper. Yes, binary star formation could spin up stars, and we see the sort of two main pathways. One of them is you have an initially massive disk that is gravitationally unstable. The GI can spin up the star by dumping high angular momentum material into the inner disk. And from those instabilities, you get companions. But also you can have companions kind of flying by the primary star, perturbing the disk and sending in high angular material into the inner disk. So these are two sort of pathways where, yeah, you can link together binary stars and making fast rotators. And I will leave it there. I can't see people, so if there is any questions, just shout it out at me.
So I think we'll start with people physically in the room first, if anyone has any questions.
I have a question. Hi. Thank you for your talk. Really interesting. I was wondering, is it possible to derive mass of a companion from this simulation, so without considering the environment analysis, just to understand if the companion can be a planet, a star, a brown dwarf?
Ah, yeah, that's a good point. It probably doesn't have to be a star. I guess maybe if you have a more massive object that would perturb the disk more, and that would create a stronger spin-up event, but you probably could get weaker spin-up events by lower mass companions, maybe like brown dwarfs or a giant in the disk. I'm not sure. Yeah, I kind of just ignore planetary mass stuff because we can't really resolve that confidently.
Okay, thank you.
Yeah.
I think I might have a slight conceptual question. I think because early on you showed sort of the spin history of various stars, and the lines, like the fast and slow rotators seem to converge shortly before you get to the sun's age. And I was
Yeah.
Does that mean we don't really know the sun's rotation history?
Yeah, so I'll just play it again. I guess we can't really figure out the sun's rotation history. Yeah, these relations are empirical to the best of my knowledge, because yeah, these crosses are observed points. So I don't think we can use this to figure out whether it was like a fast rotator or a slow rotator. It just seems like after about 1 billion years, all the low mass stars are kind of spinning at similar rates. Yeah. Maybe.
I'm now wondering if the presence of planets might rule something out. Or,
Yeah, I mean, I guess the planets would be starting to pop up around here, and then it seems to level out things. Yeah, I'm not sure. I mean, I suspect there's probably some models about like stellar winds and how much angular momentum they, you know, they can carry away with ionized particles and stuff like that. And maybe they're just proportionally more efficient with the more rapidly rotating star than with a slower rotating star. And that's why you get this convergence here. Yeah. But I think for younger stars, you can sort of do some gyrochronology. I think that is something. I'm not an observer, but I think some people try and use a spin of a star to maybe get some insight into how old or young it is.
yeah, another question?
Okay. Yeah. My question is on the possibility to form more than two objects. So instead of having a binary, maybe there is a possibility that in the disk can form a couple of stars. Is there range of angular momentum that favor this possibility?
Yes. Let me go back to here. Wow. So we can see in the low spinning simulations, we don't get as many companions, but in the higher spinning simulations, we get a lot more. And yes, maybe that could play a role in how much angular momentum eventually gets locked up in the primary star. So I'm mostly focused on the primary star. So blue is a low spin and yeah, red is the high spin. So we generally see that in the higher in the cases where we get more fragmentation, more stars forming, less angular momentum ends up in the primary star. And is that because that angular momentum is instead being locked up in the orbit of the binary? Or I say binary, multiple star companions, that potentially could be what's happening. So that's what we think is happening with the flyby. It's just this kind of exchange between the companion has like a high angular momentum. The orbit with this companion there has a higher amount of angular momentum stored in the orbit, but then as it perturbs the disk, that's basically converting some of that orbital angular momentum into angular momentum in the disk, which then gets dumped onto the primary star. But ultimately, you just got to think about this as checks and balances between where the angular momentum is being stored. Is it being stored in the orbit of the binary? So you think about our solar system. Jupiter has most of the angular momentum, or is it being stored in the star itself with the spin, or some material in between, like we see here with the circumstellar disk? So yeah, that kind of goes against the hypothesis though of binaries helping to make fast rotators, because if you have companions around, that can also lock up angular momentum in the binary orbit. Yes. I forgot the original question, but you're talking about like, sorry, do you want to repeat the question?
My question was if there is the possibility to have more than one companion, and how the angular momentum can favor this formation.
Yeah.
Or if there are other, I don't know, conditions that can favor the presence of more than one companion.
Yeah. Yes. These are, I'll have to think about it some more. Yeah, if you have higher angular momentum in the cloud initially, then you got you sort of went from getting a disk to getting a ring, and the ring would then fragment to form companions. But I guess it's again it's that same question of like where the angular momentum is being locked up. So in these low spin cases, material can fall into the inner system quite quickly, whereas in these high spin cases, because of the angular momentum, it stays further out. Yeah, counterintuitive. Hmm.
I mean, from these movies, I can deduce that if the material is still close to the main star,
Yeah, the primary star. Yeah.
is not so high, there is probability to have more than one companion.
Yeah, no, exactly. I think that is definitely the conclusion. Yeah, it depends on scales. So the thing about angular momentum is that you need to have low enough angular momentum that stuff can go into the inner disk. Because yeah, if it's not low enough, then it's just going to stay further out, and then that can fragment to form other companions. Yeah, these are the complicated things again about like modeling the spin of the star, because it's basically the spin of the star is basically the same as the spin of the inner disk, at least in the early evolution. So if the disk is spinning slowly, then the star will hopefully spin slowly. But if you can make the disk spin faster, then that will hopefully spin up the star. So the angular momentum of material that the star accretes can theoretically be anywhere between like 0 spin and the breakup spin. And that, yeah. I guess what we're trying to say here is that when you have companions in the inner disk, then that will send more material that's closer to the breakup speed as opposed to just like falling directly onto the star. Yeah. Yeah, sorry. I haven't touched this work in a couple of years, so I'm thinking about these questions again. But to answer your question, yes, if you have higher angular momentum, you'll get more companions further out. Yeah,
Okay, thank you very much.
that's okay.
This is Chelsea.
Yeah.
The question different from a different aspect.
Mm-hmm.
So if you can have one piece of observational evidence from either the current generation of instrument or next generation of instrument that you expect in the next decade,
Mm-hmm.
intuition or strengthen your current hypothesis, what that would be?
Yeah. So I guess, I mean, I am not an observer, but talking to Marina Konkul, so she's the one that was looking at the test, sorry, that's the test data. So it's from the test data that she did like this modeling of the SEDs. So like what she was saying is that, it looks like there is an unresolved companion nearby. But like just based on the SED fitting alone. So I guess any methods that would help us resolve this companion so that we can say like, yes, these fast rotators do have something nearby, and we can actually confirm that that's there. So the nearby companions, I guess they could be found through radial velocity surveys, or maybe the eclipsing binaries. Yeah, just kind of, I guess, a targeted search at these fast rotators to see if there is a companion nearby that we can detect through like RV or eclipses or direct imaging, maybe. I don't know how close the companions are.
Oh, okay, that's useful. It actually sounds very reasonable things to do.
Yeah.
From the original side. Yeah.
Yeah. I guess there's so many things to look at, and that's not really something you can do from just, I mean, I guess a direct imaging you can just get a single image, but for everything else you need to do like a time domain observations, and that's difficult to carry out.
Any other questions from the room? Anyone online have a question?
I can't see the best.
I have a question. Is my mic working?
Yes, I can hear you.
Right, okay. This is another question about your simulation. Sorry.
That's fine.
You said you don't account for radiation yet. I just
Mhm.
wanted to ask how do you think accounting for radiation would work like simulation wise, and how do you think that would impact the formation of companions and the transferal of radial velocity to and from them?
Okay, so I'm not sure about the transfer of radial velocity, but it will suppress fragmentation. So other simulations that do have radiation, but maybe not magnetic fields, the radiation just heats up the gas, and that thermal support basically fights against the gravitational contraction. So radiation definitely will we would get fewer companions than what we get here. So like one of these systems, like this one, produces 8 stars, and that's probably unlikely. So radiation will be very important for suppressing that fragmentation. As for angular momentum transport, I think it would play a role in viscosity. I think so. I need to look that up. And I guess viscosity of the gas can translate to like how fast quantities can be transported through them. If it's very viscous, then you can kind of get waves moving through it very quickly. But if it's low viscosity, you can get waves and stuff moving through the gas pretty quickly. But if it's high viscosity, then that might dampen sort of over densities and stuff, and again further suppress fragmentation. But I think yes, I'm not entirely sure how the radiation would impact the angular momentum transfer, but it would definitely impact how much fragmentation we get.
Any other questions from online? Not seeing anything.
It's okay, I've been talking for a long time, and you also had a defense beforehand, so
Yeah, lunchtime as well. So yeah. So I think thank Reggie again.
Yeah, I'll stop sharing. Thank you so much for having me. Great.
And,
Hopefully I'll see some of you at the ASA or the Hollywood.
I was going to say that, yeah. I don't know if anyone here is going to the ASA, but for those
I think
that are,
George is giving a talk at
yeah,
the
I know. Yeah, there's people in our group going to the ASA. I'm just not sure if they're here at the moment.
Okay. Yeah.
You'll see some of us there. So.
Yeah. No, it's nice to be back part of the Australian astronomy community. I'll let everyone go to lunch. Yeah. Thank you. Bye.
Thank you.
Bye.
Thanks, everyone. We'll